Fracknoy. I'm the Emeritus Chair of the Astronomy Department at Foothill College, and it's a great pleasure for me to welcome everyone to the Silicon Valley Astronomy Lectures by remote control. What we have done is to shift to virtual mode during the pandemic, and so those of you who are returning audience members, I'd like to welcome you, and those of you who are here for the first time, please join us on a regular basis. These introductory astronomy lectures are provided thanks to the support of 4 organizations: the Foothill College Physical Sciences Division, the SETI, or Search for Extraterrestrial Intelligence Institute in Mountain View, the Venerable Astronomical Society of the Pacific, and the University of California Observatories, which includes the Lick Observatory. And I want to just say a word that the recent California fires actually did threaten the Lick Observatory. One of the buildings, peripheral buildings, burned down, but thanks to the action of CAL FIRE, the main observatory is fine, and they are now assessing some of the smoke damage and trying to bring things back online. So we congratulate them for surviving this very difficult situation. In any case, we are here to present information about new developments in astronomy. I should also say that in the last month or so, one of our past speakers got the Nobel Prize in Physics, so that sets a high bar for all our future speakers. We are going to have questions tonight, I should say, and there is a notation, I hope, under me as I speak, and there will be a notation showing on the screen of a special dedicated email address to which you can send questions. And then when our distinguished speaker is done, Dr. Jeff Matthews, the astronomy professor at Foothill College, will be moderating questions and answers. So by all means, use that email during the talk to ask questions, and we'll try to get to as many of those as we can. So let me now, without further ado, introduce our speaker tonight, talking about the hunt for dark matter in the universe, new experiments. This is one of the most exciting aspects of our study of the universe, this invisible material that must be out there, but whose nature we don't understand. And we're privileged to have someone speaking about it who is involved in the experiments that are trying to pin down the nature of this dark matter. Dr. Tom Shutt is a professor of particle physics and particle astrophysics at the Stanford Linear Accelerator Center and part of the Kavli Institute at Stanford University. He has spent most of his career doing experiments to search for dark matter and has specialized in the development of instruments to do just that. He was co-founder of the LUX experiment and founding spokesperson of the new LUX-ZEPLIN experiment, which he's going to be describing for us tonight. So, ladies and gentlemen, it's both a personal pleasure and a professional privilege for me to present to you Dr. Tom Shutt.
Thank you very much, Andy, and welcome to all of you. I'd like to thank the organizers for giving me the opportunity to do this. And it's a kind of a special treat to talk to people who are interested in astronomy. My background is sort of more from particle physics perspective, because I'm looking for dark matter, assuming it's some sort of particle. And so I'm going to try a mix of talking about the astrophysical motivations for why we think there's dark matter and the way we're going about looking for one possible form of it. So let me switch over to my my slides. Yeah, so I'm going to talk about the hunt for dark matter in the universe and new experiments. Well, really mostly one new experiment, but here we go. So starting point is that we understand gravity really well. And by really well, that means, you know, if we go back to the time of Newton, we understand gravity very well. This is this wonderful diagram. Maybe some of you have seen it from Newton's Principia. He imagines a person standing on a hill. So here's a little diagram of the person, and they throw a projectile. A a certain amount, some speed, it goes to D, they throw it harder, it goes to E, they throw it harder still, it goes to F, and then you see down here, well, if you're on a planet, if you're on the Earth, there's an orbit that there's a one speed you would throw it where it just perfectly circles the Earth. And that's to balance, and apologies, I know this is a general talk, this is the only equation in my talk, but very basic physics. If you balance the so-called centrifugal force versus the gravitational force, you get this very simple prediction, if just cancel out the little m there, that the velocity goes like 1 over the square root of r. It's prediction for how much the velocity of this projectile orbiting the planet would be, what that velocity would be, depending on how far away it is from the planet. Or a planet, it could easily be the sun. So over here is what we have for the solar system. This is the speed of the planets versus the distance from the sun. And there's the dots are the data, and the blue line is just what this equation predicts, a simple 1 over the square root of r behavior. And it works perfectly well. And in fact, famously, of course, gravity locally is very weak. You and your neighbor or your spouse, have a gravitational force of attraction between you, but it's so small, it's very hard to detect. Nonetheless, people have done precision measurements. And in fact, people have confirmed Newton's formula for gravity down to the fraction of a millimeter scale. Some of these measurements are done at Stanford, but all around the world, it's been a cottage industry of making these tiny little pendulum systems and isolating them from all forces and seeing what gravity is like. And yet, if you look at the solar system, it's also working out to the edge of the solar system, which is more than 1 billion miles. So over a huge range of length scales, the gravitational relationships that Newton worked out in the 1670s are exactly, that's the way nature seems to be. And every satellite that's put up is just proof of that, because you use these equations to calculate what's going to happen. So, simple question, let's go to a bigger scale. We've seen that gravity is Newtonian on the scale from a fraction of a millimeter to 1 billion miles. Let's go to a galaxy. Of course, I think everyone at an astronomy talk knows what a galaxy is. It's 100 billion or so stars. When it's an elliptical galaxy, in this thing that is slowly rotating. And you can ask the very same sort of question. It's an object. If I'm out beyond the edge of this galaxy, I more or less see the mass of the galaxy in the center, and I have some velocity if I'm some object that's bound to the galaxy and orbiting around it. And those measurements can be done. They're not completely easy. They really came to fruition in the 70s. In fact, a woman named Vera Rubin was one of the main people who sort of really pushed this thing. So here's another photo of a galaxy, and this time this galaxy and this data down below line up. So this is the same sort of graph I showed you before. It's the velocity of an object orbiting the galaxy versus how far out it is from the center of the galaxy. And the scale of it is such that the sort of the visible edge where you kind of see the stars petering out is about here. And according to the Newtonian gravity, and it doesn't really matter if you think about Einsteinian gravity, it's the same holds here. Once you get out beyond the edge, you would predict this curve here that you're falling off, the velocity is going down, just like it was for the solar system. The details are a little bit different because the galaxy has some stuff out beyond the real bright edge, et cetera, but all that is folded into the calculation of this curve. And the data are these points up here. And there's this huge discrepancy between these points and those points. Some of it is there's a lot of gas. This is what you predict due to the force from the gas, but it still doesn't account. What's going on here is it appears there is mass that is holding on and giving the gravitational force, which is allowing objects which are orbiting this galaxy to be orbiting faster than they should. And I'm sorry, in the last slide, the 2 slides ago, I should have made the point. Of course, what's going on here is something familiar to you if you've ever been on a merry-go-round or a little, when you're a kid on a playground, merry-go-round that goes around in a circle real fast, right? If it spins real fast and you're trying to hold on, you need a lot of force. And the faster it spins, the more force you need. That was embedded in that equation I showed you. So out here beyond the edge, something is allowing objects to orbit the galaxy at really high speeds that just don't seem reasonable given the weight of everything in the galaxy. Then you can say, well, how do we know what's the weight of everything in the galaxy? And here, as a particle physicist, I throw my hands up and say, well, the astronomers have figured this out. We understand stellar evolution. We understand, we can look at the spectra, light spectra of all the stars in the galaxy, and we have a pretty good idea how much that galaxy weighs. In fact, a lot of it is gas, and you can measure that in different ways, radio, infrared, et cetera. And it just doesn't work. And so we think that there is mass present that is not seen. And for lack of a more imaginative term, it's traditional to call it dark matter. It wasn't glowing. But it's more than it wasn't glowing. In fact, it in no way can be seen with a telescope. People have looked and looked and looked. It doesn't absorb light. It doesn't emit light. It simply doesn't interact with light. That much is completely clear. And the amount that's there is about a factor of 7-ish more mass overall in this thing than is there in the normal matter that's in the stars and the gas and the dust. So then we can go to bigger scales still, because this problem didn't pop up in the solar system, but now we go to the whole galaxy and it pops up. Well, what about a bigger scale? And the next bigger thing in the universe are galaxy clusters. So galaxies tend to be in groups of a few, order of 1,000 or a few thousand galaxies. We're in a close cluster. Here's a famous image of a distant cluster of galaxies. The galaxies are seen in yellow. And in this image was one of the first really striking examples of now what is almost a mainstream tool in astrophysics and astronomy. That is to use gravitational lensing. So gravitational lensing is, we're the observers here who took this photo, of course, a nice telescope. There's a lensing object, which is this whole cluster of galaxies. It's a huge number of stars and a huge, 1,000 galaxies. They have a lot of mass. And if there's some object back behind them, by Einstein's gravity, you can calculate that mass will distort and bend the light. It essentially will act like a lens. So here in this little diagram, we've labeled it the lens. And then if you think, well, I'm the observer and I'm looking back, this light which was bent appears to be a source here. And in fact, a single source, if everything is exactly collinear and the lens were completely spherical, you'd get a ring of image of that source. But in fact, when everything's a little bit messy and this is not a completely spherical collection of things, you get just a set of images. And that is all these blue streaks. They are most likely of a quasar, a distant quasar. It's very early and bright and it's bluish, just that was its color. And all of those arcs are coming from one object back behind this galaxy. And then you can take Einstein's equations and you can essentially do an inversion mathematically. It's kind of like tomography. And you can ask, what was the mass of the lens required to make the one object create all these blue smudges? And it is this beautiful map here, which is sort of famous in the cosmology community. The spikes are galaxies, but look between the galaxies. There's just this overall kind of smooth distribution of mass. And remarkably, the amount of mass there, the ratio of the total amount of mass in this image to the spikes, which are the galaxies, is again about a factor of 7. So we come to this statement that sort of there's something called dark matter out there. It outweighs normal matter by about a factor of 7, and it does it on 2 very different length scales now. The size of a galaxy, it's about 10 kiloparsecs, and size of galaxy clusters, which is megaparsecs, 100 times bigger. If you go to even bigger scales still, what do you see? Well, first off, and maybe this is known to people, but we've kind of learned that the universe is made of Swiss cheese, or at least that's the way I like to think of this. This is a set of one of now a bunch of images which are taken from really big surveys of galaxies that come from people studying the cosmology of the universe. And where you see colors, those are galaxies. And where it's dark, that's absence of galaxies. And so it kind of looks to me, to my mind, like I like to think of this kind of looking like Swiss cheese, where there's holes and then there's kind of stringy or sort of sheets where there's the cheese. Okay, well, so what about dark matter? Well, this alone doesn't tell me about dark matter, although more or less. But I wanted to kind of frame things. We're looking at now really, really big scales. And the universe kind of looks like that. And so, in fact, well, I want to take even another jump and think about the Big Bang. So here's just an image. In fact, this is from the Wikipedia page on the Big Bang. And it's kind of a modern view of the way the Big Bang went. There was some starting condition that we just don't understand, where all of the matter in the universe was compressed to some tiny spot. And there was something that put it in a situation that, now it exploded effectively, expanded. And there was an early time where it inflated, and then the universe acted kind of normal after that. I want to draw attention to this point right here. This is the time at which it was no longer sort of like a plasma, where it was matter. In fact, at this point in time, the universe had changed from being weird exotic matter of some sort at incredibly high energies that we cannot attain in our laboratories today, to being normal protons. But at an early time, it was really hot, and the protons, it was hydrogen gas, if you will, but it was ionized. It was so hot, it was ionized. So what does ionized mean? Well, ionized is very familiar. It's the center of a flame. In a flame, the flame, it's hot enough that electrons are ripped off of atoms. And so you have charged electrons and charged protons if you only have hydrogen. And light, the glow of the flame. And the light actually doesn't go very far, and it hits an electron or it hits a proton, and the three of them are all kind of scattering. It's just like this little soup. And that's to the left of this time. And then things cooled down enough, and the universe became transparent. The electrons fell onto the protons. Now and it's cooled enough. It's no longer a flame. The flame went out. And the light that remained just kept going. And the rest of this diagram is that then all sorts of stuff developed. And I want to talk about that a little more, because it turns out dark matter has everything to do with this picture. Everything to do with this picture. In fact, this is a simple, I played with PowerPoint view of what that light from the Big Bang looks like. It's called the cosmic microwave background. It was famously found in the 60s. Many Nobel Prizes later, we know a lot about it. And one of the remarkable things is it's the same temperature and the same color, if you will, in all directions. I mean, it's light. It was very UV light. It's been redshifted into the radio, and it can be measured with radio receivers. And it's more or less one temperature in all directions. However, if you look in detail, it looks like this. And this is a famous result that was measured about a decade ago after heroic effort by a lot of people over many years. And at about a part in 100,000, in some directions, the light's a little redder, hotter, and in some directions, a little bluer. And what that really is telling us is that this plasma of gas, of hydrogen and electrons and photons was a little bit lumpy. It was very, very, very smooth. It was smooth to 10 parts per million, about a part in 100,000. It was a little lumpy. And wherever it was more lumpy, was a little heavier. Those places over time, if I just go back to this diagram, as we go to the right, wherever was a little heavier, gravitationally grabbed material from around it. Just wherever it's heavier, stuff falls onto it. Material falls onto it. Wherever it's less dense, stuff goes away. And so the contrast between what's red and what's blue just grows with time. And cosmologists have had a field day calculating this. And have we measured it well enough? Can we calculate? Can we predict? Can we predict from how we went from this picture, which is mostly uniform, but in fine detail, a little bit lumpy, to this today, where on big scales, the universe looks like Swiss cheese. And to be clear, when we say, Swiss cheese, I'm really saying empty space and very solid objects. Huge difference between the density of Earth and the density of space, which is, almost completely empty, but has some trace gas in it. Whereas in the early universe, everything was the same density to about 10 parts per million. And the answer is yes, we can calculate this. In fact, I'm going to show you a beautiful movie. I actually have to pop out from my PowerPoint over to a YouTube video. The beginning of this video is this is a simulation, and the beginning of it, it's essentially the plasma that's at one temperature. In fact, it's after it was a plasma. It's now just neutral gas. And you see a little bit of lumpiness, and I'm about to hit play, and you're going to see this lumpiness change rather quickly. But this is very early in the universe. There are a lot of people in the world that do simulations like this. This happens to be a group that, in fact, are at Stanford and SLAC that I know very well, and they did these calculations. This involves heavy-duty computer simulations because the gravitational equations are very complex. The gravity is all straightforward, but it's just the equations are complex and nonlinear and need to be simulated. And it's just a natural consequence of gravity acting in a situation like that, where this a fluid that's largely all one density, but whatever it's a little bit heavier accumulates, and wherever it was less dense sort of loses material, that the universe grows to something that looks kind of like what we have, with these kind of filaments and kind of sheets of material. And then these very bright spots, which are going to be, I think, probably clusters of galaxies at the scale of this simulation. And it's just really a remarkable success. Let me just show you this again, of our understanding of the universe, that this calculation can be done. And I just think it's a very cool video to watch. And when you do this calculation, you put in the known laws of gravity. And then the other thing you put into the calculation is what matter was there in the universe. There's this gas, right? It turns out this calculation fully does not work at all if you just put in the gas that we know about that was there in the early universe, the time of this cosmic microwave background. In fact, it completely fails. In fact, there's a dirty little secret. This calculation I just showed you, this video, only showed dark matter. Only showed dark matter. In fact, that's the only thing that's in the calculation. We can essentially understand and explain how the universe went from all of that simply through the dark matter. And I'll skip kind of the details why, but it turns out that in that story, not only is the dark matter something dark, we know that it can't even be made out of any of the normal elements. It can't be made out of the hydrogen that was there in the early bang or anything later that ever came out of the hydrogen, which is essentially everything that we know about. You know, the hydrogen formed stars. The stars finally went supernova. That formed all the elements that are in our body, the elements that are in the earth. Everything that we know about was not the dark matter when viewed from the way the dark matter played the starring role of growing the structures of galaxies that we know about in the universe. So that's really kind of an interesting thing. Not only is the dark matter, is there dark matter? Oh, my video didn't show. Very sorry. The video was really pretty, and I'm going to stop and I'm going to just show. I'm just going to do it really quickly, but I want to show the video again. So here's the video of the universe starting in a very uniform state and now evolving, and structures forming. And so this is going from an early time in cosmology to essentially the present day. And I'll let this run just once. And you know, the bright spots are either galaxies or clusters of galaxies. And it's really just an incredible achievement that people can simulate how we went from the big, you know, this measurement of the gas, the fireball from the end of the Big Bang, to today, and our mathematical understanding of the universe, it all works, except that we have to stick in that there was this enormous amount of dark matter. So one reason I also talked about the Big Bang so much is that, well, the early Big Bang was unimaginably hot and dense, very, very high energies. If it wasn't hot enough for you, go back another few seconds and it was unimaginably hotter. And if that's not hot enough, go back a little bit earlier, closer to the moment of origin, and it was incredibly hot still, hotter, how much hotter still. And the result of that is that almost certainly it had to have been that all sorts of high energy particle phenomena were present in the early universe. So particle accelerators over the last 50 years, we've created, we've smashed two protons into each other, or an electron into an electron, or electron into an anti-electron. And you can create this whole zoology of interesting particles that are heavy and exotic, but that live a short time. And so most explanations for guesses as to what the dark matter is focus on this idea that, hey, the early universe had all these weird particles in it. The ones we know about that we've studied at accelerators are all short-lived. But what if there's some type of new particle that is not common around us that we know about, but that was created in the Big Bang and didn't decay away and remains today, and that the dark matter could well be one of those particles. And so that's what I'm looking for. So let's just talk about the known particles a little bit. I don't want to talk you through this table, but particle physics has resulted in us having something like the periodic table of the elements. These are all of the particles, the fundamental particles we know about. For instance, the up quark and the down quark make neutrons and protons. So your body is made of up quark and down quark and electrons. But it turns out there's another family of very similar particles. They're heavier, they live a little while, and then they decay into those particles. And similarly, an even heavier set. Then there's these weird ghostly particles you may have heard of called neutrinos. They're incredibly small. They're actually stable, and they don't do very much, but they exist, and they're created in nuclear reactions. And then there's these particles that carry forces, like the photon. And these things called W and Z, which are heavy particles. They weigh as much as an atom, heavy atom. But the Z in particular is incredibly tiny. So actually, if the dark matter were like the Z particle, but lived, the Z particle lives a tiny, tiny amount of time, like 10 to the minus 20th seconds, it could be the dark matter. If the neutrinos were heavier, they could be the dark matter. The reason something like the Z particle and the neutrino could be the dark matter, and we wouldn't have kind of known that, is because they're incredibly small. They don't interact much. So I wanted to talk a little bit about what do I mean by a particle being small. The modern particle physics view of particles is sort of interesting. It's that all particles, in fact, the fundamental particles, the ones on that last chart, are points. They're point-like. We don't quite know what that means. It's kind of like not knowing what a black hole singularity is. We don't know how tiny they actually are, if there's some hard nugget at the center. And we haven't ever seen anything like that. As far as we can tell, they somehow have mass, but they essentially make themselves known just by their force fields. And the force fields have different sizes. So there's an electric force, and we all know about the electric force. And I've kind of colored in blue here an electric force field, which is about the size of an atom. If you give me one fundamental unit of charge from an electron or a proton, it has a force field that extends over a range about the size of an atom. To get electricity, you have to have a lot of electrons or a lot of protons. There's a force that holds together nuclei, and it's called the strong force. And it has a force field that's the size of a nucleus, which is 100,000 times smaller than the force field, than the size of an atom. And the weak force, which is not very familiar to many people, but you may have heard of in a class or something, is this other force that mostly manifests itself in radioactivity, but also in particle accelerators, we can see that it's present. And it has a force field that's about 100,000 times smaller than the strong force. So the size of an electron is really the size of its electric field. You'll often hear this funny statement that fundamentally at an atomic level, matter is mostly empty space, because maybe you have a model of an atom that has a nucleus and an empty space out to an electron. Of course, matter is not fundamentally empty space. That is absurd. If you stub your toe hits the wood, the door jamb. They didn't yield. Your toe didn't go through the door jamb because at atomic level, it's mostly empty space. The point is, it's force fields. And to say how big is something is to say how big is its force field. Why did I tell you all that? Well, the way we know about small subatomic particles is by smashing them into each other. That's the only way we can know about them, is the hard, cold fact. You can't like grab a proton in your hand and look at it. So here on the right, I have just a little cartoon of a proton. And it has an electric force field, it has a strong force field, and it has a weak force field. A proton has all three. And if I send a neutron at it, here's a neutron, it only has the strong force field and the weak force field. Most likely it just passes right by. It didn't know that there was an electric force field. As far as it's concerned, this proton is tiny. It's the size of a nucleus. An electron would say, hey, that proton's the size of an atom. If I get lucky and I'm a neutron and I just happen to hit the proton, then it'll collide off. So let me try to run those little videos again. So here's a neutron passing through by a proton. If it doesn't hit dead on, it doesn't care that the proton has a big electric force field. And here a neutron, if it happens to hit the dead center, it does. So if I have a neutrino that has this tiny force field, it sees a proton, okay, I'll say it, it sees it as mostly empty space. It totally ignores the electric field, it totally ignores the strong field. It just sees this weak field that's somehow associated with the point-like nature of the quarks and the proton. And if I get so lucky as it happens to dead on strike one of the quarks, whatever that means, it's a point-like thing, and it interacts with that weak force field, then it'll collide, which almost never, ever, ever happens. So the neutrino is a thing that has mass, but is incredibly, incredibly small because it carries a force field which is very, very small in extent. And the final thing I want to tell you is that size and mass are not related. And that is really actually one of the real interesting things here. A Z boson, which is one of the particles we know exists, it plays a big role in all of the measurements that are done at CERN, where they found the Higgs, blah, blah, blah. It weighs as much as a heavy atom, but it has only the weak force, which makes it incredibly small. The neutrino also only has the weak force, but it weighs about 1/trillionth the mass of a gold atom. So two totally different massive particles with the same size, if you will. This one is stable. It's too light to be dark matter. This one was perfect to be dark matter, but it decays in 10 to the minus 25 seconds. So that gives us an idea for what we think the dark matter could be. We think the dark matter is something that has maybe about the weak force of particle physics, which makes it tiny. It would also have gravity. All particles have gravity, and I didn't mention that, but that's basic to, in fact, Einstein figured that out. It's embedded in general relativity. If a particle has mass, it has gravity. But so then that's why it's gravitationally shows up as dark matter, but it only has the weak force, but it's heavy. And we don't really know how heavy, and it turns out we don't really know exactly how weak it would be in this theory, but it's called weakly interactive massive particle, or WIMP, which is kind of this funny name that arose about 25, 30 years ago. So how are you going to test this idea? Here is our Milky Way, artist sketch. Of course, there's no photo like this. And it's embedded, the dark matter in every galaxy isn't really kind of in the center of the galaxy. It's sort of in a big halo that surrounds the galaxy. And we know that from exactly the sorts of measurements I showed you earlier about the velocities of things orbiting the galaxy. Okay, fine. So there's the dark matter, whatever it is in this halo. In fact, here's another cutaway version. Perversely, in both these images, the halo is white, even though it's dark, dark. So if I'm a particle, so if this whole halo of matter out here is made of these subatomic particles, they are orbiting the galaxy with about the speed, we don't have to guess at that. The speed at which this thing orbits here is just given by the gravity in the galaxy. And we sort of know what that does. It essentially, it dictates the speed at which the disk of the galaxy rotates. In fact, that's the speed the Milky Way is busily rotating about the center of the galaxy. It's going to take us forever to get there, millions and millions of years. But in fact, it's not a small speed. It's about 1,000th the speed of light. So all of the dark matter here, whatever its form, is orbiting around and it's whizzing around at about 1,000th the speed of light. We also know basically how much dark matter there is everywhere. And we know about roughly how much dark matter there is on average around Earth. And it's about one of these particles per liter, which, by the way, that's a really small density. You know, another reason why dark matter is not easy to found so far is if it's kind of diffuse, it's about as dense as the interstellar medium, actually, just a gas that's randomly, you know, between stars. The reason it's 7 times more is because it just extends everywhere and there's more of it. But this gives us something to shoot for. This is actually kind of nice. I've actually said, I think I know how big it is, how physically, it's got a certain size. I've said how heavy I think it is. In the WIMP idea, it's about as heavy as an atom, a heavy atom. And I know how fast it's moving. I can predict what's going to happen. Occasionally, it will bump into a detector on Earth. Occasionally, it will bump into the Earth. Let me just stop for a second here, though. An interesting thing, if you have a weakly interacting particle, let's talk about neutrinos for a second, and you wanted to stop them, you wanted to put up some material such that the neutrino was guaranteed to run into it. I want you to think about going to the dentist and getting x-rays, right? They put a little lead apron on you to stop the x-rays from going into your organs and make it just go into your teeth or whatever, right? That apron will be maybe, I don't know, a thin sheet of lead, 32nd of an inch of lead, something like that, right? And that will dead stop all the x-rays. You can think of an x-ray as kind of a high energy particle, right? Neutrino, high energy particle. They are basically born at high energy and weird reactions. How much lead do you think it would take to stop neutrino? And here, normally, if I could look you all in the eyes, I would see anyone nodding or not if they know the answer to this. But here on Zoom, I'll give you a second to think about it. So the answer is, if you want to stop a neutrino, you don't put a 32nd of an inch of lead. You don't put a meter of lead. You need a light year of lead. Let me repeat that. You need a light year of lead to stop a neutrino. That's how small a neutrino is. Neutrino is so small that all of the atoms and all of the lead it sees as these tiny little things where it sees the weak force on the nuclei and the quarks in the lead, and it needs a light year of lead to stop it. So that's the problem trying to find WIMPs. If the dark matter is these particles, if one goes at the Earth, it's overwhelmingly likely to go right through the Earth. If one goes at a little detector I have, it could maybe bounce off of an atom in the detector, but boy, is it a rare process. So looking for dark matter consists of, in the form of WIMPs, putting out a detector. So here's a particle detector. This is something that would measure X-rays, say. If you see a movie where there's radioactivity, like the great movie about Chernobyl or whatever, and people have the Geiger counters, and they go, when those are particles striking it, and they make an electrical signal. So my business has been making interesting detectors where the WIMP would strike it, and you would sense that some energy had hit. The amount of energy deposited in the detector is rather small by particle detector standards. It's at the level of like of an X-ray, in fact, like type X-rays you'd go get your teeth done with, which is small compared to like measurements at the colliders in Europe at CERN or the collider at Stanford, SLAC. Those were like literally 1,000,000 times more energy in every particle. But you can build detectors that will do that. Okay, fine. So that's the idea. A WIMP will occasionally just strike a detector and you'll say, aha, I saw a WIMP. Well, it's not that easy. So first off, the Earth is constantly getting bombarded by cosmic rays. These are high energy particles from outer space. Actually, they come from really interesting things. They come from like supernova. They come from like the supermassive black hole at the center of our galaxy. There are these high energy protons and other, mostly protons, but other things. They hit the atmosphere and they kind of blow apart. You know, the first atom they hit, and you get a stream of particles. And the only real way to deal with that is to go underground. In fact, you need about a mile of rock to range those cosmic rays out. Okay, and in particular, it's the muons, the heavy cousin of an electron that I showed you in that table of the known fundamental particles. The muons that are created by the photons blasting apart nitrogen atoms in the upper atmosphere will penetrate hundreds of meters of rock. And so people set up in underground locations. And then they've gotten rid of that problem. And it's a real problem. One of these goes through your hand a minute. And these WIMPs are only, dark matter is only very rarely going to interact with the detector. So then the next problem is that we're surrounded by radioactivity. And here I'm not talking about radioactivity like scary radioactivity. I'm just talking about there is a little bit of trace radioactivity everywhere around us. And so we're in an underground cavern, but there's all this radioactivity coming off of the rock. So I put up a shield. And I can pick certain materials. People know how to make there are materials that are much better in not having radioactivity. It's kind of a happenstance of the chemistry. So copper, for instance, turns out to be very low in radioactivity. Silicon starts out to be really high in radioactivity, but people have been very, very, very motivated to figure out how to purify the heck out of silicon. And when you purify silicon enough to work in a semiconductor, like in a silicon chip, it turns out it's gotten rid of all the radioactivity. So we can surround the detector by a shield, and it turns out lead is not very high, is low in radioactivity, and stop most of the radioactivity from coming around. So that's how we're going to hunt for WIMPs. We're going to put out a detector, we're going to put it in a shield, we're going to put it underground, and we're going to be really, really, really careful about the materials we pick. Just a couple words about radioactivity. I made this little chart. The vertical axis is radioactive dose. And I want to give you a scale of the problem here. This here is the annual human dose on average. This going up about a factor of 100 in dose is what the Fukushima workers saw. And they were fine. About 100-fold more dose is fatal. And the poor people who put out the problem in Chernobyl got about 10 minutes in Chernobyl, which was more than fatal. Let me focus here. If you eat a banana, this is the dose you get. Bananas are a little radioactive, and it's a lot less than the average annual dose. Going down lower, our detector LZ, the experiment's called LZ, and we have a detector. We have removed, through careful shielding, all the radioactivity to get the backgrounds down to about here. But then it turns out we then are able to just get rid of the backgrounds that have the radioactive particles. It's mostly gamma rays. It's from uranium and thorium in the rock. We remove the radioactivity that hits our detector, and I'll explain that a little bit more in a second. And the problematic backgrounds in our detector are way down here. And then if we focus on the energy range where the particles the WIMPs may be, we get down here. And I just want to point out what's going on with this scale. The average normal dose you get walking around is, I don't know, what's this, about 10,000 times lower than what would kill you if you got it all in a short time. But that annual dose is something like 16 or 15 orders of magnitude higher than what we have to get to be able to see the dark matter. We are doing the proverbial needle in a haystack experiment. The hay is the radioactivity from ordinary uranium and thorium and potassium, which are the main radioactive elements. They're decaying all the time. They put out gamma rays, they put out beta rays, which are X-ray electrons. Those things kind of look like dark matter, and we have to get rid of them. So, let's talk about our experiment some. You have to go underground, and there's a few locations around the world. We happen to be in one in South Dakota in the Black Hills. In fact, it's from the gold mine that originally was the fortune that's launched Hearst. Hearst's father, not the newspaper man, his father made his money in this gold strike in South Dakota. And if you've ever seen the TV show Deadwood, it was about this mine, what became this mine. Custer's men discovered the gold in the Black Hills, and that forced off the Sioux and the other tribes after they had just been pushed into the Black Hills, and that led to the wars that Custer got killed in. Very interesting place to work. It's actually beautiful, starkly beautiful. There was a big gold mine. The equipment's from the 30s mostly, although the gold mine dates back to the 1880s or so. That's in the winter. It's an interesting place to go and do an experiment. There's this crazy thing called the Sturgis Motorcycle Rally, which is about 15 miles away. And unfortunately, these guys went and had the motorcycle rally this year. And now coronavirus is going nuts in South Dakota. But culturally, it's a lot of fun to be there. I took that photo one of the years I was there. About 700,000 motorcycles show up in this little town of 3,000 people. And just jumping ahead, this is what the previous experiment, the LUX experiment, was like. We have a detector which is about as size as a person. This is one of my students. And the WIMP is going to strike it. And we're inside of a big tank. And the tank is about to be filled with water. And in this case, the water is the basic shield. You can purify water very, very well. And then it serves as a good shield against all the radioactivity that's coming from the rock outside. This is a photo from outside the water tank. So, you know, this is just normal. Well, it's a weird place, we're underground, et cetera. But this is just normal material, full of radioactivity, water tank, water shields, the detector, and then the detector's inside. How does the detector work? The detector is made, actually, it's kind of interesting, of a big vat of liquefied xenon. Why xenon? Well, all of the noble elements actually, that's helium, neon, argon, krypton, and xenon, make wonderful particle detectors. In fact, a Geiger counter has probably argon in it, I think. The reason is that when an incoming particle strikes an atom in the xenon, it emits a little glow of light. In fact, probably most materials will do that. If a subatomic particle comes in and smacks an atom and makes it angry, often the atom will relax by emitting light, but in most materials, the light's immediately absorbed. In the noble elements, light gets out. Also, you will knock electrons off of the atoms. And in the noble elements, of course, completely inert. If you remember your basic chemistry, you know, those are the ones that have the closed shells, completely inert. An electron can't get trapped on a xenon atom or a helium atom. So we have these electric fields. We have an electric field created by, it's kind of just shown here in a light color here, a mesh of wires that are at a high voltage, and they make an electric field, and the electrons that are knocked off of atoms when the particle hits the xenon are drifted up to the top of this detector. And the LZ detector is big. It is going to have 7 tons of xenon. The LUX detector I just showed you the photo of, in the center was about a half meter. It's about a 2 foot by 2 foot dimension object that was full of liquid xenon. This is going to be a much bigger version. And we can sense where the particle interaction happened very nicely, because the electrons come up, and when they come to the top of the liquid, we pull them out of the liquid into gas, and we have a high electric field there that forces the electrons to fluoresce the gas, much like what's going on in a neon lamp, and much like what's going on fundamentally in a plasma TV. And there are these objects, these little circles here are called photomultiplier tubes. They are single photon sensitive sensors, and they measure the splash of light created by the electrons coming up out of the liquid. The initial flash of light from when the first atoms were struck also is measured in these light sensors. The time difference gives you the depth of the event, and the pattern of light from this bright flash up top tells you where laterally, in XY, if you will, the event was. And so remarkably, in a huge tank of liquid xenon, we can measure an event. We've only put sensors on the top and the bottom. The sensors are always a little bit radioactive. So our challenge in removing radioactivity is reduced to just getting the xenon clean, the radioactive sensors around the perimeter, and yet we've measured events everywhere in the xenon. And it turns out it's relatively easy to get xenon very clean from radioactivity, because as an inert element, there's these simple purification techniques that just take out any junk that would be in the xenon, and it's in the gas. It's easy to purify gases compared to like a solid, like a metal or something, which you have to melt and do stuff with. And gas, you can just start working with immediately. This is what the data looks like. This is a candidate dark matter event in the LUX experiment, the previous experiment. So this is time here. It's 200 millionths of a second. There was first 2 photons measured from this first flash of light, and then a bunch of photons measured from the electrons creating the second splash of light. The time difference from here gives us the depth. The pattern of which PMTs were hit, which is kind of this number over here, tells us where it was. This could have been a WIMP, but unfortunately, this was actually calibration data. We can simulate the WIMPs, and this was from the calibration data. But just, I think it's kind of an exquisite technological thing that in this case, it was 300 kilograms of xenon. We could measure this very low energy interaction that created 2 photons, and this is probably about 5 or 10 electrons which created this signal. This very, very faint ghostly interaction, and we measure it very well, and we know where it was. And again, the radioactivity is all around the periphery, and we look in the center of the detector, and that's clean, and we can look for our WIMPs there. And even a little bit more detail than that. I know I've given you a lot of detail. This is kind of the last detail I've got. When a background gamma ray, so the gamma rays are from radioactivity. When they strike an atom, what happens is they knock an electron out of the atom at high energy, and that electron goes careening around like a, I don't know, like a just trail of destruction, bull in a china shop. This is a computer simulation, a Monte Carlo simulation of what happens, and all the spots in blue are where another atom hit hard enough to create lighter charge, scintillation or electrons. And this whole thing is in a very small, this is microns, if that's a millionth of a meter. This is about 1% the width of a human hair is the total range of destruction from this event that gave me the charge and light that you saw in my last slide. The dark matter, by contrast, let me take a little space here that's very small, much smaller than my percent of a human hair, blow it up. The same energy dark matter creates a similar looking kind of path of destruction, a little different in detail, but the main point is this is an incredibly small scale. This is about the width of 100 atoms. All the destruction, all the energy is confined to a small space compared to here. The WIMP events are much denser, and that gives us a difference, coming back to this image, in the amount of initial light and the number of electrons which give this second flash of light. The ratio of electrons to photons is very different simply because the density here is very high and the density here is low. So here's our the data from the LUX experiment. I divide the amount of light charge by the amount of light, number of electrons divided by the number of photons on an axis here, two different plots. In the top, we calibrated the detector by taking in a deliberately bright source of radioactivity and putting it near the detector, or actually in the detector. In fact, we dissolved tritium into the detector and then took it back out. And you see that we get all these events, the black dots. Each black dot is from a quote-unquote event, some particle decay in the detector. And they're between these two blue bands. Then we calibrate the signal, the dark matter signal. Neutrons are a radioactive background which also interact with, like the WIMPs do. What they do is they strike the nucleus of an atom instead of the electrons in an atom. I'd forgotten to say that, but that was the difference to give a different track. And so the dark matter or neutrons striking the nucleus of an atom they make less charge compared to light, which is just a consequence of the density of the whole thing being different. And this population is well below this blue line. This blue line is the center of where these events are. This red line is the center of where those events are. The dark matter will fundamentally look different than gamma rays. And it turns out we can essentially, the neutrons are rare in radioactivity, and this is really our problem and not the neutrons. So the final data from the LUX experiment, which is from 2013, had this final data set. Here are the data, all the little X's are events of unknown origin. It's a smear. Some of them spilled over into the potential dark matter band, but if you just look at this, all of them are at the upper half. If there were dark matter present, it would be centered around the heavy, the central line. And so sadly, after a lot of sophisticated statistical looking at this is incompatible with there having been dark matter in the detector. This was the world leading result when it turned on, and was a world leading result for about 3 years. There have been a whole bunch of experiments like LUX looking for dark matter. In fact, I have been doing this my entire career. The first experiments were in the late 1980s. They looked very different than this experiment, but basically they did the same thing. And here we were, we got a crack at the apple. We took our chances, but we didn't see dark matter. So we're working on a bigger experiment. This is the same water tank, much bigger detector. I showed you the other kind of cartoon of it. This is actual, computer automated design drawings. We've added an extra layer of shielding. This is a active detector in and of its own right in green. It's a cheaper type of detector, and it's going to deal with neutrons. And we're still on this water shield, but it's a much bigger experiment. It's 10 tons. I've spent the last 5+ years, in fact, 7 years, I would say, working on this experiment. I mentioned the fact that you need these electrode meshes to create high electric fields. So that's something that my group at SLAC did. Here's a woven mesh of stainless steel. It's kind of boring to talk about. It looks like a screen door, but it was a huge, huge effort. It's to do this. All these materials are very radioactively pure, et cetera, et cetera. We did a lot of testing. So here we are testing a prototype of the detector. This is a long, skinny version of the full detector, and we basically learned how to elements of how to design those grids with this testing. And there's the detector. So this experiment, LZ, has not turned on. It is about to turn on. This was last winter, just before COVID hit. We had assembled the detector. I didn't really tell you the walls of the detector, which were sort of hidden in my images, are made of Teflon, which is highly reflective. And so this is you're looking at a bunch of Teflon, and on the other side of that is where the liquid xenon will go. This is about to get placed in a ultra pure titanium vessel that is cooled down to -100 degrees Celsius, which is what you need to liquefy the xenon. Here you can see the array of photomultiplier tubes. These are cables to read out the photomultiplier tubes. There's something like about 700 or 800 photomultiplier tubes in the experiment. We did a lot of work to make sure there wasn't any dust. So it turns out a good way to look for dust is UV light. So here's an inspection of the thing. We've actually very rarely did we uncover the detector. Almost the entire life of all these parts, they were covered in plastic bags, except when we took a publicity photo and when we put the thing in the vessel. Here we are looking for dust in a slightly uncovered area while the rest of it is covered in plastic. There was a lot of that sort of activity to keep the radioactivity low. And one other kind of fun thing is, and it's a SLAC, one of our group's things, is removing krypton from xenon. So, xenon is nice and inert, and xenon has got no radioactive isotopes, it turns out. Krypton, which is another noble element, has a radioactive isotope, krypton-85. It actually comes from more or less from the nuclear industry in France, but a little bit from the nuclear industry worldwide. And it's in the air. It's not really harmful for people, but it's way, way, way hot compared to what we need. And when you get xenon, which by the way is purified, it's distilled out of the air, which is a whole interesting story, but I won't go into, it'll have krypton in it. And we use a technique called chromatography. We mix our xenon with helium, and we pass the cocktail of xenon and helium plus the unfortunate trace amounts of krypton through a column of charcoal. And the xenon comes out slowly, this is time, and the krypton comes out fast. And this is a generalization of something that's called chromatography, which is used in chemical analysis you may have encountered in chemistry lab. And this can separate the xenon from the krypton. And this is a big plant we built. We have a lot of students in our group. This is mostly students. This is actually, I have a partner who's another professor at SLAC, Dan Akrib. He and I run this group, and we have this big chemical, call it a chemical plant we built. That's a charcoal column. That's a charcoal column. There's some massive pumps around. And in fact, at this moment, while I'm not on the phone, while I'm not online here talking to you all of us involved are watching this. This plant is busily processing. We have 10 tons of xenon, and we're taking the krypton out of it. We're removing it down to something like 50 parts per quadrillion. 50 parts per quadrillion. That's less than a part per trillion. And at that point, the krypton won't be radioactive at a level that matters. This is how we talk about our results. On the vertical axis is the size of the particle. We call it a cross-section in particle physics. Essentially, if two particles are going to smash into each other, in this case, the WIMP on the xenon atom, how sort of big did they look to each other? A typical nucleus is about 10 to the minus 23 on this scale. So we're here about 20 orders of magnitude smaller than a nucleus size. The horizontal axis is the mass of the WIMP. A GeV, that's particle physics jargon, that's the mass of a proton. 100 proton masses, that's just an element in the middle of the periodic table. And this is a kind of range we don't really know. Any one experiment, so LUX is the blue curve here, didn't see anything and excluded this huge space up here. If the WIMP was effectively bigger, it would have scattered more often and we would have seen it. We didn't see it, and so we're left with knowing that it's less than this. The state of the art worldwide right now, from a set of experiments which have been neck and neck for some time now, and we've been leapfrogging each other, is these three lines. The xenon 1 ton is a little bit out in the lead. On this log scale, it's only a little bit out in the lead. LZ and the successor to xenon 1 ton, we're racing to turn on, and we're going to get down here in this range. Kind of the mean expectation is we're going to get down here at about this black line, and this green and yellow line is because we have a lot of computing power nowadays, and even while we're building the experiment, a lot of smart people spend a huge amount of effort thinking about the statistics of what we might see, and this is kind of the statistical fluctuations we might get, like when you hear about voter poll and has a certain uncertainty. Modern experiments think very carefully about the statistical variations we might expect, and it turns out to be surprisingly broad. But if the dark matter is in this area here, we're going to see it. This gray area is kind of it's a kind of a way to try to say where some theorists, not some theorists, where kind of consensus opinion in the theoretical community of particle physics, they're the ones that came up with this WIMP idea. They're the ones that think it's sensible to think there's a new particle that's weakly interacting and about as heavy as a gold atom. They're saying that it might be in this gray area. We're including some possible models that were now ruled out by LUX and Xenon N-ton and his Pandex experiment in China, but it includes all these things that we can maybe go find. This orange bit is an interesting thing. About a decade ago, even though people had been at this for about 20 years, we stopped and realized that neutrinos from cosmic rays, I mentioned the cosmic rays, from particles hitting the upper atmosphere, though that process creates neutrinos, those neutrinos occasionally will interact in a detector, and technical details, but they interact with the nucleus just like the WIMPs. We can't get around the floor of neutrinos, and we're approaching it, which is to say, if dark matter is in the form of WIMPs, we may well see it in this next big bite we're getting with the experiments which are just about to turn on. If we don't see it and we go a bit further, another factor of 10, and still don't see it, we will run into an irreducible background that will not allow us to look further. It's not quite irreducible, but in practical terms it is. And so if it turns out the dark matter is of this story I've told you, weakly interacting massive particle, and it lies down here, sadly, we're not going to find out. On the other hand, it does kind of mean we're not going to be like Captain Ahab forever. And I have been at this for 30 years and we haven't found it. So I'm kind of comforted by the fact that we eventually have to stop looking. I do want to just make a point here. I'm talking on behalf of a large number of people. The LZ collaboration actually has over 200 people now. A lot of good friends of mine, a lot of young students. This was a meeting we had. It's an international collaboration. One of the groups is from Portugal. This is from Coimbra in Portugal, where it's like an 800-year-old university. Wonderful to visit. We had a meeting there. But this is how science is done, big collaborations. Also, I didn't really talk about it, but of course, there are other ideas for what the dark matter might be, other types of particles, et cetera. Well, especially other types of particles. And so there's a whole world of people looking for the dark matter if it's a different type of particle. But until now, for the last 20 years or so, people have thought the WIMP was the most likely story. And the biggest experiments, the biggest ongoing experiments have been looking for WIMPs. And this is, so LZ is about to turn on. It's going to be an exciting time. So in summary, we know there's dark matter. We don't know what it is. These weakly interacting particles that would have been made in the Big Bang that are analogous to particles we know about from standard, particle physics are a good guess. If it's WIMPs, liquid xenon detectors have emerged as the way to look for it. And it's now exciting time because two major new experiments, which effectively have 100-fold higher sensitivity than what's been done before, about to turn on, and 2 order of magnitude in this sort of space of how big is the WIMP it's a big deal to get an advance at that scale, and hopefully we're going to find the WIMPs. But if we don't, we're soon going to reach this neutrino floor. Okay, and with that, I think I'll finish the talk. We can go to questions.
So why don't you stop sharing the screen and let me, in the meantime, thank you for this amazing talk showing us the forefront of technology. I'm going to encourage people to use the email that you see on your screen to send questions to Dr. Matthews, who will in a minute read them, but I'm going to take the moderator's privilege to ask 2 quick questions. First of all, when, as reasonably as you can estimate, when do you think LZ will actually start taking data? And the second question is, do you have any preparations for success? When we search for alien signals with the SETI project, they always have a chilled bottle of champagne in case there's a moment of success. Do you guys have any preparations for success?
Yeah. When will we turn on? Before the coronavirus hit, we thought we would be turning on really about now, this fall, around now. Actually, given the nature of the race between the experiments, we've kind of gone radio silent on that. We are several months delayed because of the coronavirus, but that's all we're saying publicly. But it is imminent. It's not 2 years from now. Let's put it that way. What will we do if we? Well, yeah, we'll go to Disneyland and pop the champagne. More seriously, if we do see the particles with LZ, that'll be really fortunate, because the next thing you'll want to do, it's kind of obvious. If you hadn't seen them in the previous experiment, given how much bigger LZ is, best case we'll see on the scale of like 30 or 40. If we were to see more than that in LZ, then they should have shown up before. And that's a little bit marginal. That'd be pretty good. But if we see like 5 or 10, you really would like to see hundreds. Now, what will certainly happen is everyone in the particle, in all of physics, will get super excited. And absolutely, we will suddenly have money showered down upon us to build a factor of 10 bigger detector, without a doubt. And we've all been thinking about how we would do that for a very long time. And in fact, almost certainly the next experiment will be a combination of our experiment with our currently rival. Because when experiments get to a certain size, it makes more sense to work together. It's so costly. So we would immediately start on that big detector. And fortunately, if we do see something in LZ, with that extra decade before the neutrino floor starts to be annoying, we get a pretty good look at it. And then, of course, you'd be trying to look other ways. You would certainly redouble the efforts at CERN to see evidence for the particle physics that would also they would go hand in glove with the WIMP story. because in fact, we were hoping to see evidence for something called supersymmetry at CERN, which was one possible reason why WIMPs would exist, and such evidence wasn't seen. That doesn't rule out the WIMP story, but if we saw something, it would redouble their efforts because they would expect maybe they're going to see something. Now I could go more into why you would think there's that connection, but there's that hoped for connection between what we're doing and what they're doing.
All right, thank you very much. And again, thank you for the talk. I'm now going to introduce Dr. Jeff Matthews, who's the astronomy professor at Foothill College in Silicon Valley, and he's going to moderate the questions from the audience. Jeff, take it away.
Thank you very much, Andy. And thank you, Dr. Shutt, for coming and speaking with us this evening. Great talk. I would also like to thank all the people who have sent in questions, far more than we will be able to get to this evening. And so thank you for sending your questions to astronomy@foothill.edu. And so let's go ahead and dive into those. I think we have time for 8 or 9 questions. And so the first question from Neil is dark matter likely to be many different kinds of particles or just the one?
No one knows. No one knows. It's everyone's guess. Let me give you 2 views, though. There's an Occam's razor view, which says, boy, if there's some new form of particle, there's probably one of them. That's kind of simple-minded, and we could fluff it up in fancier language. There's another point of view which says, if there's another, we're guided by what we've learned in particle physics to date. And in particle physics to date, new types of particles have tended to show up in families of particles. Now, the WIMP story in the particle physics world comes from a theory called supersymmetry. And in that theory, actually, there would be a whole bunch of new particles, but only one of them would be the dark matter. So in a lot of models, you would think it's one particle. It's still fashionable for people to say, well, but maybe it's got several components, because, you know, much of physics has been kind of messy and complicated. So, but the truth is, we don't know. It's you know, it's kind of your prejudice and belief. We have to do the experiments to find out. If we're, God forbid, if we're lucky to find that question out.
All right, and another question here from Chris. We have, what is the observationally determined limit on how strongly light could interact with dark matter?
Ooh. That's a really good question. I don't really know the answer directly. I mean, I'll just say this, right? People have invested enormous amounts of money in telescopes because they want to see stars, and they want to see dust, and they want to see gas, and they've measured in radio, they've measured in infrared, they've measured in UV, you know, huge amount of astrophysics and astronomy, almost all of it carried out by looking at photons. Nothing has ever shown a hint of the presence of the dark matter through its interaction with those photons. So to put a number on it, I don't quite know how to do it, but it's a pretty super well-established fact. Certainly no version of normal matter. There is no way to take normal atoms and hide them and not be the dark matter. Let me be a little careful there. If you put normal matter into certain types of really dense planets, or like white dwarfs, or, as I was always asked, black holes, you wouldn't see it via the way it interacts with light. And there's other reasons that we don't think the dark matter came from normal matter. But certainly you can't put it into sort of normal atoms and sort of hide it in a galaxy. That cannot be done. I'm not an astronomer, I don't have all the details at hand, but they assure me that that's absolutely uncontrovertible.
Your answer there anticipated the next question I had queued up, which was to ask, could it be that it's black holes?
Yeah. So that's a really interesting question, and especially with the black holes being so abundant as seen by LIGO, which was a bit of a surprise. How quickly LIGO saw 2 black holes coalesce, and now the huge number of black holes coalescing they've seen since then. I don't know if you guys know about the LIGO story, but that's a whole cool thing. Okay, there are a lot of black holes in the universe. Why dark matter? It turns out, I think the statement to be careful is we don't definitively know it's not black holes. One thing is certainly true. Everything we know about stars, and the normal way you form black holes is you have a star and the star collapses and has an explosion and what's left behind is a black hole. Those can't be the dark matter. Because my story, which I know was kind of abstract, and I thank everyone for their patience with my movie I didn't actually show. That whole story is fascinating and complex and tells us that at an early point in the Big Bang, the normal things that became all the neutrons and protons and all the normal matter cannot account for the dark matter, no matter what happened next. So normal matter in a normal way, forming stars, forming black holes, cannot account for dark matter. If black holes are the dark matter, they actually had to have been made at some super early time in the universe in some exotic physics that we simply do not know, that created black holes at some early moment in the Big Bang. That is solid. So people talk about quote unquote primordial black holes. It also turns out if you try to take the mass of a galaxy and multiply it by 7, because that's the amount of dark matter, make it black holes, they actually aren't very benign. Just gravitationally, they'll be like, you know, they're orbiting, they'll go through the galaxy. Basically, they'll jiggle the stars gravitationally. And that's one thing. And there's other things they do. And in fact, that's kind of not my field of expertise. There are talks that go on and on and on, and they show black holes from being very, very small to being very, very, very large. And various techniques have ruled out most versions of a black hole that came from some weird primordial time as being the dark matter. But it's actually an active, you know, one year there'll be a paper saying it can't be black holes in this mass range. And the next year someone's like, no, those guys were wrong. And then 2 years later, other people are like, no, they were right. And it's not quite settled, but it doesn't seem likely. And it's not, people think about it actively, but most versions of a black hole aren't allowed.
And so then there's one more black hole related question, which is, could dark matter get pulled into black holes once they do exist? And so do the regular black holes end up being kind of mixed matter black holes?
Yeah, absolutely. No, there's certainly black holes pulled in dark matter. That's the case. The thing we know about dark matter, and I didn't really bring this out, is that it doesn't appear to interact in any way. And normal gas and dust, in the same way that like coalesce to form stars and planets, on the galactic scale, a big accumulation of stuff that, you know, I showed how like that we can simulate how stuff grows, you know, through gravitational collapse from these huge scales down. And when a galaxy is formed, the normal matter kind of coalesces down to the spiral disk, and a lot of it's in the center. What is true is the dark matter, because it doesn't interact and can't lose energy, kind of stays out more on the perimeter. But absolutely, you know, there's a supermassive black hole in most galaxies, and probably the center of every galaxy. And for sure, those have sucked up a lot of dark matter. And I'm sure theorists would love thinking about that.
So here's a bit of a technical question. So you talked a lot about dealing with radioactivity from your containers and instruments and whatnot, but what about things like heat from the electronics? Do those cause problems with vaporizing the liquid medium?
We had to carefully design the way the liquid xenon works. In fact, that's a little specialty of mine, is cryogenics. I love cryogenic engineering. And there's a lot of thought put into it, and we had to pay attention to it. It wasn't fundamentally that hard. We don't have a lot of electronics, actually. But we have a bunch of cooling. The cooling is provided ultimately by liquid nitrogen. And we actually have a little liquid nitrogen plant underground, which you can buy a liquid nitrogen plant if you have a spare 100K. You can put one in your backyard and have a lot of liquid nitrogen.
So here we have a question that's sort of zooming back out again. A question about from Anne about the halos of dark matter. Are those just big spherical structures, or are they flattened like the galactic disks?
Really good question. What to say? So the answer is they're not flattened. They're probably again, this is not my real world of expertise. There's astronomers and astrophysicists who think a lot about this. The claim is that they're typically football-shaped things, but there's a very basic reason. The fact that they don't interact, and it turns out the fact that they can't emit light, whereas normal matter can, is the fundamental reason why the normal matter, which probably at some early time was kind of in a more spherical thing, was able to collapse down to a disk by emitting light. And I know that sounded weird and I didn't explain it, but there's a whole backstory to it, which actually I probably can't explain, but I've been told it many, 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 many times. So the dark matter is a kind of a non-interacting thing. Its gravitational collapse kind of sucks it in, but realize when things gravitationally collapse, they speed up. And so now they're still moving, and that gives the size of the sphere. The normal matter has energy relaxation mechanisms by emitting light, and that's why the galaxy, the normal matter, is kind of collapsed down more and is in a disk. So the dark matter is not thought to be in a disk. It's a bit model dependent, but you also know from these studies of the dynamics of the galaxy. In fact, that's how you first figured it out, that it had to be spherical or football shaped. And then from that also people kind of have this explanation about not emitting light and not interacting, and therefore they can't collapse down to a disk.
All right, so we have time for just a couple more questions. And so we will take a question from Anand asking, when you talk about a particle hitting another particle head on, is there some threshold of their fields that you're talking about there? Like, is there some clear threshold?
I'm not quite sure what you're asking, Anand. It sounds like a good question. I mean, so it's these two kind of fuzzy force fields, and what it tends to mean is if here's one particle and here's another particle coming at it, and they can kind of have a glancing collision, or they can have a more head-on collision, and that's just, it's going to affect how much this particle banged that one as it moves on. And you can have a glancing collision where this one just gave this guy a gentle nudge, or you can have a more head-on collision where this gave that one a lot of energy. And it also is the case, and maybe this is what you're asking, there tends to be, some distance away, basically nothing happens. And it's a little different for the different forces. The electric force is kind of a little fuzzier. The strong force has kind of a very firm distance. And if you're a little bit outside that distance, nothing happens. Electric force, it's more like what I first described. Although even for the electric force, finally, if they're far enough apart, nothing happens. And the weak force is kind of like the strong force. It's got a really finite range. You either are in that range, it's like BBs, as opposed to like, cotton balls, if you will.
All righty, and so we'll have our final question here from Susan, asking if you could just give a quick summary. Why is this hunt important for our big picture understanding in astronomy? So I'm thinking here, like, how do the different possible results that you find for the nature of the particle end up affecting our astronomical understanding?
That's a really good question, and that okay, let me play a cynic for a second. From an astronomy point of view, maybe you don't care. Maybe you don't care. From a physics point of view, where, maybe it's a little bit the difference in kind of interests of maybe a pure astronomer and a pure physicist, although I don't think people are ever that. But, a physics question would be, do we understand the nature of matter? Do our equations understand the nature of matter? And the fact that the dominant form of matter is a particle or some type of matter that we haven't understood, for physics is this huge crisis. It's like this huge hole in our understanding. We think we understand so much. We understand the four forces. We understand the Big Bang. We understand subatomic particles. We can You know, we understand electricity and magnetism. We understand quantum mechanics. We brought you Silicon Valley, right? Physics did that. And yet we don't know what the main form of matter in the universe is. So for us, it's just disaster that we don't understand this. And interestingly, in the early days, astronomers were happy with the idea that there was dark matter, but very much resisted the idea that it could be a different form of matter, because they're not used to particle physicists are always making these weird forms of matter and accelerators. At this point, everyone understands that the universe is dominated by dark matter. And in fact, I think, you know, most astronomers, in fact, all astronomers think dark matter is a huge, huge issue. Philosophically, do you really care that you don't know what it is? Yeah. And a final point, I mean, I think most people do, but you know, that's a taste issue. One other issue is, though, we have been hoping, and this is actually more the astronomers, we've been hoping that something about the behavior of galaxies would somehow be able to be modeled where the dark matter wasn't treated purely as a thing that only interacted by gravity. I mean, I kind of didn't quite say that in my talk, but it's really true. A lot of things in astrophysics, the behavior of galaxies, this thing orbiting that thing, whatever, need dark matter to explain how the galaxy worked. But the modeling that puts the dark matter in, puts it in and says, all that dark matter does is interact gravitationally. And we have all been hoping that in the astrophysical sense, something would show up where, oh, the dark matter, you can tell that actually at a very faint level, it's colliding with the normal matter, or it's colliding with itself. That would give us some clue as to what it is. So in point of fact, trying to understand the dark matter, it's kind of it's a marriage of astronomy and physics, because you can't even think of physics wouldn't have come up with the problem without astronomy. And probably the solution is that it's a new form of matter, and that's kind of the domain of physics. And the two to come together, you know, and that's the hope that we can, you know, the depressing thing is if we never figure this out, you know, that might happen, right? I mean, I'm having looked for 30 years and not found it. I've been on a set of experiments that all had world-leading searches, blah, blah, blah. We haven't found it. So I'm just hoping someone finds it. It'd be great if it's LZ. If someone else finds it because it's a different form, I'm still going to be really happy.
Thank you very much, Dr. Shutt, for this wonderful discussion. And I will just say, as an astronomer, that just as much as it's a slap in the face of the physicists that you don't know what fundamental parts of matter are made of, I think we astronomers consider it a slap in the face that we only know 1/7 of what the universe is made of, as you said. So we wish you the best of luck with this experiment. And thank you again for coming and sharing it with us. Let me say to the audience, thank you for participating. Usually if we were meeting in person at Foothill College, each of the members of the audience would have received the program with information about the 4 organizations that support this lecture. But in the absence of that, I would encourage you to go to the About page of our YouTube channel, where there are links to each of the supporting organizations where you can find out more about the good work they're doing. And I want to invite everyone back. Our next lecture in this series will be Wednesday, November 11th at 7 p.m. Pacific time. And our featured speaker will be Dr. Michael Brown of Caltech on the possibility of finding a major 9th planet in distant reaches of our own solar system. So we look forward to seeing you again then. And that concludes this lecture in the Silicon Valley Astronomy Lecture Series.